work in this UA1, UA2 experiment. And he worked in these careers in the Orsay, also in this university of in the Nijmegen University, sorry, the pronunciation, but he spent most of these careers at CERN. You know that that's the main part of this thing. And I just said a few words about him, other than all the details. He was the co-author of the book, co-author of the paper which is written combining the CMS and Atlas detectors. What is the synergy? What is the difference? How the two different kind of detectors give the same kind of physics? I would request all of you read these papers. And also here's a paper of this hadron colliders, handbooks on particle physics. And in 2010, I think he gave a lectures in this room, almost a similar topic. And I was so impressed on that talk. This time, when we selected the speakers for this school, I insisted this IOC that he should come for these lectures. So I hope you will also be impressed with these lectures. With this word, I'm calling Daniel.
Thank you. Thank you, Govinda, for your kind words. So good morning, everyone. I'm going to try and be as slow and as pedagogical as this wonderful talk you just heard, introductory lecture from Emil. I will contradict, however, Emil on one small point, a little bit as a joke, a bit later in the talk. So I'm not sure exactly, like Emil, exactly what I was supposed to talk about. I'm going to talk about, since you have specific lectures on gaseous detectors, on silicon detectors, semiconductors, etc. I'm going to talk to you about the more global picture of how you build a large-scale experiment at a collider, what are the ingredients you need, and how this actually worked for the LHC. I'm going to use often the example of Atlas, because I worked in Atlas all my life, since '84. So I started working on Atlas when I was about 30. I would say older than most of you already at that time. And I worked on Atlas for about 40 years up to now. So this is a huge part of the useful professional life of a human being, of course. And you have to be motivated that you will actually be able to profit from all the work you put into this to actually see some hopefully wonderful things during your lifetime as a professional person. So this is an example here of a true photography of Atlas when it was being installed. Now, if you go, all of you, most people who come to CERN over the past 10 years, you see this a bit like a closed cathedral. You see it from outside. It's almost like if you're in church, you have to believe that inside there's a real detector, because you don't see it. You see pipes, you see cables, you see shielding, you see not very interesting stuff, and very interesting stuff, which is the pieces of the detector are hidden inside, even the external detectors. So in principle, this is built from a series of 5 lectures. I will somehow try to condense and skip some of the parts for which you have other lecturers who will give you more detailed talks. And I will today take you through a sort of introductory, a bit historical lecture. So in the history of particle physics, if one, so I think I'm going to go a bit quick there, because you heard already from the previous very nice lecture a lot about this, but there were a set of discoveries which happened, many of which gave rise to Nobel Prizes, and famous names which we all know in particle physics, which we learn about. In the history of instrumentation, which is something somewhat different, there's also a set of famous, let's say, steps forward. Actually, you saw some very nice pictures, like the cloud chamber, bubble chamber, etc. And Freeman Dyson says something which, to me, I find very important, is that new directions in science. So this is about the balance between theorists and experimentalists. In France, we are brought up in a very Cartesian state of mind. There's no room for doubts. You don't learn about uncertainties in university at France. Everything is certain, you write equations. So essentially, if you don't become a theorist, you think you failed at something. If you become an experimentalist, you're a failed theorist. This is, of course, not really true. Need both, as I will show you. And here is another way of better saying this. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. And this is really true if you think through these statements. Our hope was that the new tools and technologies developed over more than 20 years to build Atlas CMS at HCB, at least, would lead to exciting discoveries at the LHC. I can tell you I'm very lucky in my professional life because when I was 30, we discovered W and Z boson UA1 and UA2. This was already an incredible piece of luck to live this yourself as an experimentalist. And then many years later, we discovered the Higgs boson. So twice lucky, like squared probability. So I hope some part of this luck will also happen for you in the future in whichever very beautiful experiments might happen, which are not even predicted today that they will happen. If one looks at something about Nobel Prizes, it's a little bit biased, I would say, if one is an experimentalist. So it sort of confirms a bit the French bias about theorists versus experimentalists, because Nobel Prizes for instrumentation, there is a list here, but if you look at the list, the gap between the last Nobel Prize and the one before it is like many, many years, like more than 20 years. And since then, there hasn't been one. And George Sharpak, who I knew personally because I lived in his house as a student, renting a cheap way of living. He rented part of his house to a community of people. When I talked to students already in 2007, 8, they didn't know him. They had never heard of him. George Sharpak, who's a fundamental person for all the gaseous detectors which we build today. He invented the concept of multi-wire proportional chambers and many other things. So I will skip things about bubble chambers. You saw examples before. This is another example of the discovery of the sigma zero. I think you didn't show this one. So it's yet another example of how on one picture you can perhaps discover a new particle. And here is I put in this slide just now as a little bit of a joke in answer to what Emil said. So here is a slide of the first events we saw for the discovery of the Z here in UA2. So the Z is this peak here, but there are some events here, you notice, before one selects more strongly on the electrons. And then if one selects strongly, one gets only these events. So one is almost sure without needing to do complicated calculations that this is a peak, a new particle. For the W boson, it's less obvious, right? Because you measure only one. So there's a question about this. You measure only one particle of the decay. So it's supposed to have what's called a Jacobian peak. So a peak at half the W mass. But when you have few events, you don't really see a peak. You see something fairly flat. So we heard in the pipeline, across the young people talking between the experiments that Carlo Rubbia was going to announce the mass of the W based on 5 events. So many of us thought, me in particular, this is crazy. 5 events with this spectrum measuring the mass makes no sense. And then someone who was more sensible went and wrote a small likelihood function and measured the mass with an accuracy of a few GeV. Here, the spectrum extends over 10 or 12 GeV, but if you do a likelihood fit to a shape you know what it should be, you get the mass within a few GeV. So actually, it's a theorist who said the opposite of what you said. He said, Fermi himself said, 1 event is a cross-section, 2 events is a mass, and 3 events is an asymmetry. It's a very nice statement. And of course, this can be disputed. So I will try to show you an example of something which, because of course, what you said in your lecture is absolutely true. You need to prove that you have a signal by showing that the background, the probability for background is negligibly small. And I will try to show you an event which is almost sure to be a Higgs event a bit later on. In a sense, it's the best category of signal to background in the Higgs boson searches we have. I'll show you it a bit later. Okay, coming back to what led us to the technologies we run today in Atlas and CMS, which are already out-of-date technologies because they were designed in the 90s. So like by now, 30 years ago, some small parts have been upgraded, but only very small parts of the detectors in both Atlas and CMS. So the drawback of bubble chambers, let's say the killing one, was that they had a very low rate capability, a few tens of events per second. And the LHC, as probably many of you know, we have a billion collisions occurring every second. In addition, they cannot be triggered, the bubble chambers. They cannot be sort of triggered to focus on something which should be more interesting than the average. So you have to look at all the garbage events. At the LHC, we cannot even save to disk all the garbage events. We can only save like maybe 10 to the -7 of them to disk. So one can also wonder, all the events we throw away, is there some new physics in there? Well, we try to make our trigger such robust enough that it's not the case. And of course, human analysis of photographs is very tedious and very tiring. So in the 70s, electronic detectors took over. And once you have that, you can start to think seriously about designing a detector. And this is the first time this happened in history for the LHC detectors. And that's why they were so successful in the fact that they behaved as expected when they saw their first data, is they were simulated with a precise knowledge, not only of the particle physics, so the Feynman diagrams and all this, this is one part of it. You have to simulate and show to committees, to funding agencies that, yes, I will discover the Higgs boson if it's there for sure in a few years. No, you also have to convince yourself that what you're building will actually be able to do what you say it will do. So for this, you need to know the physics of interactions of particles in matter with a very, very fine-grained resolution and a very precise accuracy for all the processes which can happen. So if you imagine a bunch of particles which are essentially, as you heard in the first lecture, essentially they're going to be pions in a hadron collider. They're going to be charged and neutral pions. So you'll have gamma rays, soft gamma rays, many charged pions, which enter your calorimeters, which go through your tracking detectors. And you have to somehow be able to simulate every single interaction of every single particle in every single layer of your detector. This means you have about 10 million volumes in Atlas to describe the detector, 10 million volumes in the picture of the geometry, which we capture for the simulation. And then with a program which everyone uses called GEON4, which needs to be constantly upgraded in its knowledge of the physics, microscopic interactions of particles in matter, we simulate these particles, we track them step by step through the detector, all the way across the detector, which is 50 meters long and 25 meters high. So you can imagine this is a huge amount of CPU, a huge amount of lines of code, a huge amount of human effort to produce it, validate it, and then also to follow its grid computing and all that. I heard that here you also have a lot of computing facilities, so people here are aware of the amount of work it is to get this working. And what we need to achieve is something which is accurate to, let's say, 5–10% of reality. So we also need to know what we built. So this is where the engineering work also came into Atlas and CMS, which was never done before, that we filled tables with the knowledge of every single material and the weight of every single material and the position before we actually operated the detectors, and we filled that in, and we used then integration programs to measure the weight of the detector as it should be in the simulation, compare it to the weight of the detector when we installed it. When you produce a detector which has a huge amount of different components, it has the sexy parts like silicon detector or a carbon fiber structure, which is supposed to keep it stable to microns over a lifetime. These are very sexy to do for engineers and also for particle physicists. When you have to think about cooling the detector, when you have to think about cabling the detector, it's less sexy. The electronics chips are also very, very huge activity, and electronics engineers, microchip designers, they love to produce ever more powerful computer chip, electronics chips for silicon detectors, for example. If you ask them to produce a table of the amount of material you need to cable them up to their power, they are much less interested in doing it. And so you have the risk of underestimating the cost, the effort it takes, and also the amount of material you end up putting in the detector. When you're naive and you want to show that you have no material, for a particle physicist, the ideal is a detector which measures everything infinitely precisely and weighs zero. Then there will be no interactions inside the tracking detector, or the tracking detector itself, and the particles will arrive like virgins in the calorimeter. But of course, reality is not like that. So electrons in ATLAS and CMS are far worse measured than they could be if there was no material in front. So the big difference in resolution between ATLAS and CMS electromagnetic calorimeters, which is a factor of about 3 in just intrinsic resolution of the crystals of CMS versus the liquid argon sampling calorimeter of ATLAS, this is almost lost for, let's say, Higgs to 4 electron decays. You don't see this at all in the resolution of the peak because it's dominated by material effects in front. So all of this to say that it paid off to actually do all this work, because when we looked at our first data, contrary to what people feared from the Tevatron, for example, where at the Tevatron, the CDF and D0 detectors and their upgrades were not built with such a huge effort of simulation before, and they had big surprises when they took their first data. They had difficulty in triggering for neutrinos. How do we trigger on neutrinos? We trigger on neutrinos because, as you heard, something is missing. We don't measure them. So something is missing, at least in the plane perpendicular to the beams. We have some missing transverse momentum, and this is a way to trigger on the presence of a neutrino or a supersymmetric particle, for example. So in ATLAS and CMS, we had no problem running missing energy triggers from the very beginning, because basically the detector operated as we expected. We had some problems, of course, but they were overcome very quickly during the first months of data taking. So particle detector simulation at the very precise level requires even to put into the simulation the shape of the electric fields you have in detectors in order to capture the signals which are produced by the particles which interact. One example of such a program is Garfield, which is able, in a sense, to even produce one by one the electrons in the avalanche near the wire, where you get let's say, the size of the signal, which in the end you will be able to extract, amplify, and send out to your readout. Another thing which is related to particle detector simulation, which evolved there very positively, I would say, and it's fortunate for the LHC experiments that Moore's law was quite true for a long, long time. I think it flattened out after the 2000, but essentially Moore's law was computing power doubles every 18 months. And another law, which I call modern world's law, is the use of the human brain for solving a problem is inversely proportional to the available computing power, which is a bit unfortunate. The more computing power you have, the less you think. However, in the design of LHC detectors, we had to use both the human brain and Moore's law, because we never have enough computing power in a sense. Today, still, both ATLAS and CMS suffer from lack of CPU power to produce enough events for all the physics they want to do, despite the huge resources we have. So all this in in a nutshell to say that the knowledge of the basics of particle detectors is really essential to, if you want to live this experience yourselves, to participate in the construction of a new detector, a new experiment, and then profit from all this work to do the physics, interpret the physics. As experimentalists, we're also allowed to interpret the physics. We don't necessarily need the theorists for that, for simple interpretations. And then also, which is the most exciting part, which we are living now at the LHC, is to interact with the theorists to further develop the tools we have to understand better the data. So, yeah, I'm going to skip that slide and go a little bit to a parallel of theory and models. There's been a whole set of history also up to the Glashow-Weinberg-Salam model, which you heard about earlier in '67, which is the basis for the standard model as we know it today. And along this path, this is the representing from Greek mythology, the interaction between theorists and experimentalists. So this is the experimentalist, the theorist is watching. The experimentalist is pushing a rock up a slope to build an experiment, to do a measurement. The theorist waits, publishes some papers, and then at some point, the experimentalist reads through the result, and then the theorist has to work and produce some calculations. Of course, this is a simplification. It happens all the time, but I would say that my experience twice in a lifetime with the UA experiments and with Atlas and CMS is that theorists like to, maybe some theorists here will disagree, but they like more to work on new physics like supersymmetric processes than to work on, let's say, hardcore NQ-bellow QCD calculations of standard model processes, which is the level which we need today. And okay, this is understandable too, because it's not so hard to produce maybe a new model to respond to some LHCb flavor universality problem than to actually compute at order alpha S cube all the diagrams, which are tens of thousands, which contribute to Z boson production at the LHC. So the theorists, they have progressed a huge amount. I don't know if I have time to talk about this in these lectures, but over the 10 years of the LHC, we went from something which was not even quite next to leading order QCD for predictions of physics of all the processes which are of interest at the LHC, from the Higgs boson to top quarks to Z's and W's and diboson pairs, all that stuff. Supersymmetry too, but it doesn't seem to exist, so I don't mention it. But supersymmetry is also known to next to leading order for many of these non-existent processes, as far as we know today, unfortunately. And this has been where this is so fruitful, when you become alive in the experiment, that you understand your data and you know what you want from the theorists. And the theorists then listen, because you show, here is what you produced. It doesn't agree with my data. I need something better. Then they listen and they go back to looking at the basics and helping a lot with improving the calculations. And this is very rewarding for everyone. So this little loop, which is endless, can be looked at for astronomy and for Higgs boson in a similar way, right? You have an apple which falls from a tree, you make a model with a certain equation, and then you can predict the position of the planets in the sky. And then the next generation of experimentalists, they measure the position of the planets in the sky. And then you perhaps have to, not this law, which doesn't change, but you have to refine your model of the orbits of the planets and compute things better, because suddenly a new planet appears and, there was something wrong in the calculations, etc. And this is how progress goes. And okay, for the Higgs boson, it's the same. You heard why the Higgs is necessary. In a nutshell, you will hear more tomorrow, I'm sure. And in the end, we did discover this one, and we were hoping to discover these, and we're still waiting. And there are some theorists who still believe it's possible to see supersymmetry at the LHC in some well-hidden or stealthy way, in the way it's produced, because it's not produced in the most natural way. This word naturalness you hear a lot in theoretical talks about new physics. Okay, another thing which is remarkable today is the huge success of the standard model in particle physics. I hope I'm not stealing your thunder of tomorrow. The predictions are in agreement with the measurements up to per mil level in many places. Actually, the best measurement in terms of precision is the magnetic moment of the electron, which is in agreement to 11 significant digits between theory and experiment. A huge achievement of both, right, to achieve this level of accuracy. And of course, one has discovered the W, the Z, the top quark, the neutrino tau, the Higgs boson, etc., after prediction by theory. These were all discovered after prediction by theory. So actually, with measurements already existing, one was able to guess a little bit where they were in mass without being very precise necessarily. And then general relativity. This is cosmology, totally different field. Predictions, again, are in agreement with measurements to 0.1%, broadly speaking. I'm not an expert on this, so I'm not going to defend it very strongly. However, these two are still incompatible from a fundamental theoretical viewpoint today. So this is the one thing on which people, of course, still actively work. So since the dawn of time, humankind has been wondering about the elementary constituents of matter. Going back to Greek mythology and philosophy, 4 elements before Christ. Then Mendeleev, 19th century, more than 100 basic elements. And now, now, at the time of Bohr and Rutherford, which you heard about, beginning of the 20th century, 2 basic elements only. And now we have a bit more, but it's still not as many as Mendeleev. So if you now picture the standard model the way you saw it in the table, but with animals which have a weight which is proportional to the mass of the particles. So you have the neutrinos, which have mass, which wasn't discussed much yet today, which is another hugely important experimental discovery of the last 25 years. And then you have very heavy particles, the heaviest one being the top quark, which is this big killer whale. And the Higgs was not yet found when this slide was made. So it should be an animal which is in between the weight of these two. So I guess maybe an Indian elephant, a very big Indian elephant, or I don't know what. Another thing about Higgs. So when I was making lectures many years ago, we didn't discover the Higgs yet. So the only example of a Higgs was actually Mr. Higgs. And another thing about the Higgs boson is it was with us for many decades as a theoretical concept, a scalar field linked to the vacuum in a more refined way. The dark corner of the standard model, even for some theorists who were teaching the Higgs mechanism, it felt like some kitchen cooking, which was maybe not so convincing. And as a joke also, an incarnation of the Communist Party, since it controls the masses, right? So this was a joke actually made in Russia, in Crimea at the time, a long time ago, by a well-known theorist. And for me in particular, it was a painful part of the first chapter of my PhD thesis. So yeah. And so if you ask me, please show me a Higgs boson. Here is one, I would say, with only a small probability for this not to be true. The signal to background for such events is about 30. So there's a very good probability that this event is a Higgs boson. And what allows us to say this with such a high probability? Well, first, it's the best signal to background in terms of decay. Higgs to Z star to 4 muons, 4 leptons, which are the red lines here. So 4 muons measured, very hard muons measured across the whole detector. They traverse the detector almost like neutrinos. They just produce EDX. And then there are 2 additional, 4 actually jets. One of them is even B-tagged. Not sure that means much, but there are 2 jets which characterizes as being produced by WW or ZZ fusion and not through gluon-gluon fusion. So this makes the production process sort of more robust in terms of probability of background events simulating this. And this is why the signal to background is so high. So it's called in our jargon a VBF production mechanism with a Higgs to 4 electron decays, vector boson fusion. I can't do better. So how do you get to produce a nice picture like this? Because what you have is this Higgs to 4 muon decays. Okay, this is not very nice graphics, early graphics at the time when we were simulating these events. This is the signal event, which means you have the 4 muons from the Higgs production, and you have a few soft particles which are produced as part of the remnants of the protons, which gave rise to the gluon-gluon hard scattering, which produced the Higgs boson. But really, because we are at high luminosity, the event looks like this in CMS. In this case, it's a CMS representation, because you have to add on top of what you saw before, about 30 uninteresting events with many soft particles. And it's not very easy to extract this. And over the years, even at the very beginning, we were able to do it. And as the years have gone on, we have improved and further our abilities of how to do this. And this was really needed because the amount of pileup of extra proton-proton interactions which are happening at the same time as the one we're interested in, at exactly the same time, these are by now at the level of 60. We're taking data now at the LHC with 60 extra collisions. This is a huge load on the, in particular, the tracking detectors. It's very difficult for them to keep the same operational point of how they operate with the best properties and still be able to cope with such a load of data transfer, of single event upsets in the electronics chips, which cause them to produce nonsense results, etc. Here is an example which I showed in 2011. So it was not very long after the start of the LHC. It was a bit before the Higgs discovery. And we were at the level of 14 pileup events per bunch crossing. So what one of our colleagues did was working on the data preparation of the experiment. He sort of thought, maybe I should produce a picture of a Z boson event, which everyone knows we can see without problems. So here is a Z boson decaying to 2 muons. And this is the vertex. So this is along the beamline. And you see the tracks here in that direction in the inner detector. They're just straight lines. The magnetic field is solenoidal. So they're straight lines, and you see many tracks pointing to this vertex, and you have these 2 hard muons. So the algorithm in ATLAS and CMS is almost the same. Among all these vertices, these other vertices here are represented as little colored dots, and they represent these extra minimum bias interactions. So you have as many tracks or more tracks coming from some of them. But if you're clever, so if you say that the vertex I'm going to define to characterize the event is the one where I have the largest sigma pt squared of all the tracks. So you add their transverse momenta squared. These 2 have 50 GeV each. So they completely win over all these others, which are very soft tracks. And that's how we're able to actually identify the primary vertex of interest with a very good probability, at least when we have tracks from the hard scattering. If I have a Higgs to gamma-gamma event, it's much more difficult. So I have to do something more clever. But at least in many cases, the tracking detector alone can say to the calorimeters, here is where it was the primary vertex. If you think about it, this is very important, because if you want to compute the missing transverse energy in the event, this means you have to now look in the calorimeters outside the tracking detector. So in these parts of the detector where you measure the energy of the particles, and you have to look at jets, for example, coming from quarks or gluons hadronizing. And these jets, you have to assign to them direction at a primary vertex, which if you change its position, this will change the missing transverse energy in the event. So it's very important to be as able as possible to define this early on in the software rather than have to recalculate everything at the end. Okay. So to carry on a little bit, so how does one really extract, these are general things about a signal from a Higgs boson decay? Since the Higgs boson was sort of the candle with which we were comparing ATLAS, CMS with each other experiments which were proposed before ATLAS and CMS were approved, we had to prove all the time how well can you do for every single possible mode of detection of the Higgs boson. So if you think about the basic fundamental mechanism for producing the Higgs boson, it's this one. So it's a complicated loop diagram, which took a huge effort from the theory community to get it to a control level where it was accurate enough at the level of what we measure today to predict the cross-section for Higgs boson production. And here you have the decay into a real Z boson and a virtual Z boson and 4 muons. And what we know about this is that basically the Higgs boson mass before we found the Higgs was above 114 GeV from the lab machine and the experiments. So the 4 muons, unfortunately, are very often produced, more often produced in processes like this. So this is production of 2 Z bosons, and I have 4 muons again with similar high transverse momentum coming from each of the 2 Z boson decays. And this is often called an irreducible background because it has the same final state as the signal. You cannot distinguish the final state in this specific case. There are additional reducible backgrounds, so backgrounds where it's not a Z boson here, but it could be a pair of top quarks which produce 4 muons. But the muons there, some of them are close to hadronic jets from the top decay. So it's a reducible background. They're not all isolated if you have 4 muons from TT bar production. So what we have to do is essentially extract from this event here the mass from the properties we measure of these particles, the mass of the parent particle. We hypothesize that there's a parent particle and we compute its mass. And with that assumption, then we can produce so this is all simulation, right? This is before we had data for Higgs mass of 300 GeV, what we would expect to see after a few years at the LHC as a signal above the background I was telling you about. This irreducible background does have different kinematic properties than the signal, so you can reduce it to some level, but it's still not that small around the peak. But with enough data, you can easily go to funding agencies everywhere and say, I have discovered the Higgs boson, if that were the case. And this is actually what happened. So at the beginning, this looks like looking for a little bump, very little bump under a huge pile of damping factors, which are background. But in the end, it turns out to be the cleanest signal we have at the LHC for Higgs boson. In the days before we took data, we had these wonderful pictures of our just built detectors. This is the CMS tracker in a barrel silicon detector. So you see no cables, no connectors, no connectors, of course, but no cables yet, and a lot of stuff missing before it's ready to be installed. And the same with the ATLAS pixel detector in 2006. And the one big thing we didn't know is, would these detectors operate for many years in a stable way? Now we know. Even the gaseous detector in the inner tracking system of ATLAS, to which I worked a lot, the transition radiation tracker, has survived beyond the expectations and will be removed, fortunately for itself, because I don't think it would stand the HLLAC and be replaced by a purely silicon detector in a few years. But in those days, we weren't sure whether these detectors would actually behave as expected, as hoped for, and they did. Okay, so I don't know how much time do I have?
10 more minutes.
10 more minutes. So I think I'm going to skip this. This is just before we operated the LHC. These are old slides. So let me beginning a little bit on the environment really which we face when we have to operate these detectors at the LHC. So starting with the accelerator, we have a wonderful magnet system, which was in itself a huge technical challenge. These superconducting dipoles, which were called 2-in-1. So since we have not protons and antiprotons, you need two different lines for each of the particles because you want to bend them in different directions. And this is a huge complication initially and was solved in a very nice way with these LHC dipoles. So no one talks about it anymore. And here is a representation of the magnetic field actually achieved by these magnets and of the cable, the superconducting cable, which was used to build them. That's one of the magnets. And the giant challenge of the LHC was the biggest challenge to me, at least, also talking to some of the engineers of the machine, is that with this type of energy and number of particles circulating in the beam, it's quite difficult to explain to general public when they come and visit CERN and they say, you produce all these protons, how do you do? And I tell them we have a bottle of hydrogen and we know Avogadro's number. So it's 10 to the 23. So actually the protons, it costs 0 for the LHC, the protons themselves from a hydrogen bottle. What costs is to bring them to this energy. So several accelerator complexes. What costs is to cool down, of course, to almost absolute 0, the vacuum, and then to operate the machine. And what you have as a risk is that this stored energy, which is huge in the two beams, it's similar to the energy you need to heat and melt 1 ton of copper. If you dissipate it in 88 microseconds, which is the time in which during the LHC bunch train, there is a gap where if the machine wants, they can extract the beams and send them to be dumped in a beam dump. Then you have to dissipate 8 terawatts. And the world's capacity today, electrical, is 3.8 terawatts. So this is a really daunting task. People worked for years and years to build a system to extract and dump the energies of the beam in a way which was safe. One could also express it in terms of bombs. Another thing which I discussed with one of the main engineers of the LHC was, so if one asks, he was asked this question at a conference on large-scale electrical devices. He was asked, what is the efficiency of the LHC? So he didn't know how to get the answer, so he needed a particle physicist to help him. So we decided that we would calculate this in this way. We'd say 100 Higgs boson should be enough to say that we have seen the Higgs boson. This is let's say the efficiency. I've reached my fulfillment if I find 100 Higgs bosons. And I take 100 times the mass of the Higgs boson. This is the energy for having being satisfied. And then the total energy provided by EDF and the CERN network, etc., can be calculated by him, not by me, to be 140 megawatts during 2,000 hours, 100,000 gigajoules. So you get 10 to the minus 20 efficiency. If you go to a conference of electrical specialists building large devices, they will laugh at you and say, you're not in business. This is not financially sound at all. But okay, of course, the answer to that is that it's not a laughingly small efficiency. It's an incredible tool produced by humanity and unique to improve our understanding of the fundamental properties of nature. And we produced this actually, this calculation when the LHC had just turned on after the accident in 2008. So that's why this photograph of the beam is back and light is again there. And that's how the 4 detectors looked like as they were installed. And maybe I would stop here for today and continue tomorrow with the rest of the lecture. Thank you.
Thanks, Daniel. Yeah, actually, we expected this lecture from you. Dedicated lecture will be coming from the others.
I'm sorry?
We expected the lectures, what you outlined you. So that's the we expected from you.
Okay, thank you. I'm happy.
Yeah. So any question?
Please don't be shy. Huh? It's
Yeah.
nice for us to interact with you.
Can you go to slide 32? 32.
You want me to go back to slide
Slide 32.
32?
Yeah.
This one?
No, next one. Beam dump. Yes.
This one?
So I was just curious, how do you means dissipate this much of energy? Means what kind of engineering goes into this stuff?
Okay, so yeah, it's a good question. I don't know if I would have been able to design such a thing. So it's like a huge, there's some extraction magnets which sort of deviate the beam into a special tunnel under the Jura. So it's sort of like below a lot of rock. And in there, the beam is allowed to, it's forced to increase in size so that the energy is dissipated over a larger area. And it goes through successive amounts of heavy material like tungsten, lead, I'm not sure exactly, like many meters, so that the energy is dumped. And of course, this becomes radioactive material very quickly. And at some point, some of it melts and it has to be changed and taken care of safely. It's a whole issue, of course, of terms of radioactivity.
That's Daniel. Okay.